Okay, welcome back. So we're in a new week, another week, our third together, and so we're on a Tuesday lesson about algebra, and we're going to pick up basically where we left off last Thursday. So if you want to watch the videos that led up to this on algebra, you can find them in a playlist on the channel. We've talked about different aspects of polynomials, degree and form, and behavior. Multiplication, addition, simplifying, and today we're going to talk a little bit about factoring. The first thing I want to do is establish factoring as, in a lot of ways, undoing distribution. So let's take an example here of 3 times 2x plus 3. So remember, this is an implied multiplication right there. It's 3 times 2x plus 3. I think I might have said minus, but plus 3 is what I meant. And if we were simplifying this, we would execute the multiplication where we can and rid ourselves of the parentheses. We get 6x plus 9. Okay. Now, what I want to focus on for a second is the fact that this equal sign is two directions. It is bidirectional. So left is equal to right. Right is also equal to left here. We've established this equal sign. And notice what's happening here. If we go this way, we're simplifying. We're actually executing 3 times 2x and 3 times positive 3. If we go this way, we're doing something else useful called factoring, right? Here we're factoring out a factor of 3. What does it mean to be a factor? We have to be in common, right? So let's just immediately jump into another example. Let's factor 15 minus 3a. So you want to just start to take your time, but say you're looking at common cross terms. Is there anything common that could maybe divide out? So for example, there's an a in this, but only in the second term. There's a 15, but only in the first term. But there's a 3 in common here because 3 divides 15 and 3 divides 3. So this is equal to 3 times 5 minus a single a. And be careful, you established that 3 is in common here. You want to factor it out. That means it comes out of all places, right? Because that's how you establish 3 to be a factor in the first place. And now you can look this way. We factored this way. We did simplification. We did some multiplication like last time. So we're going to do a bunch of examples today. And I want to give you a little bit of time on each one to think about them to decide, can you factor or not? How would you factor? Okay, well, hopefully you notice some things. First, they're both negative. There are only two terms, the negative 20y, the negative 5z. They're both negative. There's an addition of the two of the terms, or you can think about it as subtraction of 5z plus negative 5z. Those are interchangeable. Y and z neither show up in both terms, so they're going to be stuck where they are. They did not result from a distribution or can't result out of a distribution. But 5 and 20 do have something in common. They have 5 in common. So we have a negative in common. We have a 5 in common. When we pull those out of there, we get this. Negative 20y minus 5z is equal to negative 5 times 4y plus z. Times 4y plus z. So I think we did a decent job in the previous videos of establishing why we simplify, why it maybe is useful to simplify. And it's interesting right now because we're kind of doing the opposite of simplification. Part of our strategy for simplifying was to execute operations where we could. So if we started on the right here, we would want to execute the multiplication and actually go right to left here and say, you know, negative 20y minus 5z, that's the simplified version. And that would be true. But if you're thinking ahead about why factoring might be useful, think about this. We've done addition, subtraction, and multiplication. Now we're moving to factoring before we're going to talk about division of polynomials and simplifying those. You might see or recognize why we might want to talk about factoring before we talk about division. Okay, how's this one? Trying to factor that. All right. Z isn't in common. 6 isn't in common. 2 seems to be in common. So you could think, okay, let me do this. That would be an adequate factoring. It is in fact factored, but often we want to factor as far as possible. So what we might notice here is that the parentheses here on the right still have something in common, a 5. So if we take that 5 out of there, we get this. Of course, if I'm going to write the equal sign, if I'm introducing the equal sign, I need to be producing something on the right-hand side that is equivalent. All three of these are equivalent to each other. Plug in any z you want, they give out the same value. But some are simpler to look at, some are in forms that may be useful to move forward. (39u minus 52v plus 13). So there's a way to speak yourself through it, and I started it in the previous question here of kind of, you'll start to recognize things. If you know, all the terms are even, then you can pull out a 2. You know, so if you can pull out a 2, maybe then you look at 4 or at 10, see can you pull those out. So are they factors of 10? Well, yes, 10 and 60 are. But in this one, you know, I usually start with the smallest number coefficient, so 13 in this case. And I think about, can I pull that number out? That's always the first thing I look for, because if I can, that's going to be my best case scenario, right? That's going to factor out of everything. And in this case, in fact, I can. All three of these numbers are factors of 13. So 39u minus 52v plus 13 is equal to 13 times 3u minus 4v plus 1. So take that same mentality. Yes, so you might notice, oh, they're all even. They're all also multiples of 10, so I could factor out 2 or I could factor out 10. But I'm going to start with the smallest coefficient. Absolute value of it is 40. Does 40 come out of all of these terms? Yes, it does. And therefore, that's going to be likely my best that I can do for factoring. Noticing that b and c and d are only in one term, so they don't get to factor out. A similar question here, 40bc minus 80c minus 40cd. Now we're thinking about what's in common. Well, still the 40, but also a c. So we take out 40c. So you can kind of get a sense of how this all comes together. Let me erase here for a second. Of course, if you ever think to yourself, oh, he erased that too fast, make sure you just can pause the video on replay and you can look at anything that I have had written for as long as you'd like. Let me zoom back in here. And let's take a look at factoring. Five y squared plus y. Now we look at coefficients. Well, 5 and positive 1, nothing in common there. Technically positive 1, but you can pull that out infinitely many times and it doesn't affect the terms, because multiplication by 1 or division by 1 just yields itself. But we can also look to the variables, right? I pulled out a c in the last one. In this one, pull out 1y. Y times 5y plus 1. Remember, this is always checkable. Because we've established the equal sign is two directions, left to right or right to left. Both are equivalent to each other, no matter what direction you want to think about it. So going from right to left after a factoring will check it for you. If you execute the distribution correctly, you do y times 5y, that's 5y squared. Y times 1, that's plus y. Oops. Let's factor 3a minus a to the fourth. Oh, it's very similar. So we are undoing a distribution. Undoing a distribution. Okay. Now, the larger idea here for the first stage of our factoring learning is a concept called grouping. So this concept lets us, well, it's probably best to look at an example actually, and you can see what grouping lets us do here. We're going to try to factor p times q plus 2q squared minus 7p minus 14q. Now what do we have here? What we have is a situation where we have four terms. Some of them have likeness to each other, right? There are some terms with q, there are some terms with p, there are some terms with multiples of 7, some terms without. When we group, we want to look for pairs or triplets, but usually pairs, that have enough in common that we can factor. So what happens here is kind of interesting. So I won't reorder in this case, and I'll look at the first two terms here and say, what comes out of that? Well, they have a q in common, and what's left there is p plus 2q. And then I look at the second two terms and say, what do they have in common? They have a minus 7 in common, and what's left is p plus 2q. So I'll pause right there. So what did I do? I looked at this group of 4 terms and said, let me split it up in my mind into 2 groups of 2 terms. Do those 2 groups of 2 terms, they have something in common within them? Yes, the first 2 do. They have a q in common. The second 2 do. They have a negative 7 in common. I can factor those out as usual, with the kind of tricky moment happening right here, where I factor out the negative 7 from the second 2 terms, but it's not multiplication times the q times p plus 2q. It's not times negative 7. It's actually minus 7 times p plus 2q. So there's a tricky thing happening there. We are factoring out, and there's still this sense of addition and subtraction being really key here. You're adding and subtracting 4 terms. You factor. Now you're adding and subtracting 2 groups of 2 terms, of factored terms. And what happened here is something that can happen that's quite great here, which is that now after we've done grouping and factored, those are in common. So I think you can see at this step here, if you were to distribute the q and distribute the negative 7 in their rightful places, you would go back up a line, right? You would be back to where we started. So that's important. Anytime we're establishing this equal sign, that has to be true. What we have done to the expression needs to be maintained. You need to keep an equivalent expression, though it looks different. Now this is an interesting moment here, right? Because actually now we're looking at 2 terms. Yes, I've been calling them 2 groups of 2 terms, so they're pairs that we've done some grouping and some factoring out of. But now think of this as 1 term. Think of this as another term. Well, they have something in common. They have a p plus 2q in common. And what's left is q minus 7. Okay, this is an important and difficult question, and it's one to spend some time on here. Let's do a couple more that are somewhat similar that may hopefully illustrate what's happening here. So let's factor 6a to the 4th minus 3a cubed plus 4a squared minus 2a. Okay. Well, let's approach it similarly. Look at the first 2 terms. Do they have anything in common? Look at the second 2 terms. Do they have anything in common? Well, yeah. The first 2 have 3a cubed in common. What's left is 2a minus 1. The second 2 terms have minus 2a in common, and what's left is 2a minus 1. Now check for yourself. What we're doing is allowable, because if we were to multiply this bottom line out, it's a double distribution, sometimes referred to as foiling. We get the second line, we get the top line, right? They might not always, depending on your steps, look identical. This is the idea. And it does, in fact, show that these are equivalent expressions. We have factored properly because when we multiply back out, we get back to the original statement, this one. Okay. One or two more of this type here. Let's do I'm just picking some examples from a few worksheets that I found online here that are useful. So you can always, if you're looking for more practice, maybe search for worksheets online. There are many. You can search, be specific in your searches. I search, for example, polynomial factoring worksheets, and so many come up, so you can just look through and pick a couple questions to do. Or you can use your textbook, also a great resource, but if you've exhausted that, useful to look online. So the first thing here is to recognize this as one. It has 4 terms, so grouping may be relevant. What I want to do is actually do this in 2 different ways. So I'm going to take the first 2 terms. What do they have in common? They have a b. Second 2 terms, what do they have in common? They have a 2d. Okay. What I want to show is that there are multiple kind of routes to the same answer. But for example, if this was actually rewritten like this, so hopefully you notice that these two are equivalent. All I've done is commute the middle 2 terms, and because it's addition, we are able to do that and say they are equivalent. They are. Now let's do some grouping. I'm noticing a mistake in the previous work there. Kind of beneficial that I was doing this to illustrate the example. So this has minus 2c in common, b plus 3d. So you can see that, via factoring, we get the same thing. So the terms have been rearranged, but we are, in other words, we are allowed to move terms around in order to get them together so that we get 2 groups of 2, say, that do factor in obvious ways. Now we can recognize here this is particularly important if, say, you have it like this. Because it doesn't quite work out the same way that we would want, because the first 2 terms have nothing in common, right? Only a single 1. So factoring out a 1 is irrelevant. So we are able to slide the terms to say, well, okay, b squared and negative 6cd don't have anything in common with each other, but b squared does have things in common with the last 2, and so does negative 6cd. So let's separate those 2 and pair them up differently. We're allowed to do that only if it's this simplified version, right? There are no parentheses. We're allowed to slide terms, commute them via addition. Okay, rather than doing, quadratic factoring, which we can leave for Thursday, let's do a couple more of these examples. Now again, what are we doing? We are undoing distribution. I want you to keep that in mind here for factoring. It may seem arbitrary, but we're undoing a distribution. So in some ways, we are organizing a division. We are executing a division, but it's via factoring. So it undoes a multiplication, but it doesn't actually remove the factor in any way. We'll see that in future lessons, what that might mean, where it may be, maybe you've seen it, maybe it divides out top and bottom. So a couple more examples. Let's do one simpler and one more complicated. So here's one that, if you are following along, hopefully will work okay. You want to factor that. QR plus 3R minus 5Q minus 15. Okay. So it's a good example that just illustrates what grouping is all about. It goes from 4 terms, 4 individual terms down to 2 pairs of 2 terms. Let me actually clear this out because this one may take me a little bit more space. Our final example for the day here. M squared n minus 5m squared minus 9mn plus 45m plus 8n minus 40. So 6 terms. Okay, we're trying to factor 6 terms. Well, still group into pairs of 2. If they're already, I'm kind of analyzing them in steps here. I'm looking at the first 2 terms and the next 2 terms and the next 2 terms as pairs. The first 2 terms have anything in common? Yeah, they do. There's an m term in common. The next 2, also an m term. Looks also like 9 and 45 has something in common. The last 2 terms, 8 and 40, I know have something in common. So let me reset here. Okay. Yep, I knew I was doing something wrong there. So it so happens, oftentimes we encounter questions in our math classrooms that set up so nicely here. We are able to group. They are going to have the same term in each of the 3 groupings, n minus 5, and therefore we can factor that out as well. And factoring that out there from the second line to the third line is undoing this distribution that's on the third line here. Now, as of today, I'm comfortable stopping right there. But what we should be ready for Thursday is that this actually distributes factors a little bit further. We're going to be talking about factoring quadratics of this term, of this type. Actually factors one step further like this. Okay, so if you're here today, great. If you're here today, that's awesome. If you're not, Thursday we'll talk about that even more. Thanks for stopping by. If you're needing some geometry help, go ahead and stop by tomorrow. Otherwise, I'll see you Thursday for algebra.